Up will be an axiomatic basis for computer programming on the relaxed ARM-A architecture, and Angus and Zongyuan will present.
Thank you. So, yeah, we're going to talk about a technique for reasoning about programs in very relaxed settings. So we want to be able to do this because, of course, all of our modern hardware architectures, many of our modern programming languages exhibit weak behavior. In particular, we focus on the sort of very relaxed ARM-A user mode setting. And the good news is we do have an authoritative model for the authoritative memory model, for user mode ARM-A. The challenge really is we want to be able to do our reasoning in some sort of a computational way. Whole program reasoning can be very challenging to scale. So if we want to reason about large programs, we want to be able to do it bit by bit. And the ARM-A model is extremely global, which makes that quite challenging. So to start, just by quickly looking at the kind of shape that can make this reasoning difficult, this is the load buffering example. It's sort of dual to the store buffering example we saw in the last talk. We have a pair of memory addresses x and y, which are both initially 0. And we have two threads, each is going to read from one of those locations and write to the other location. Write a 1 to the other location. And perhaps surprisingly, the ARM specification allows for the execution where both threads read a 1. To see why this is an issue, I want to briefly look at what sort of properties we expect to have in a compositional reasoning tool. So there's lots of things you might want, but at a bare minimum, we want some ability to take the sort of reasoning resources that we have at a program point and pass them through to the next program point and continue using them to reason on the same thread. In separation logic, this is largely captured by the frame rule, but there's variance. And we also want some ability to pass resources from a store to a load that reads from that store. There's many different mechanisms you can use for this, but you need something or other because you want to be able to take the synchronization that your program does operationally and reflect it logically. So what's the issue? Well, if we have both of these two properties, and we look at the load buffering example again, we can see that if we use the first property to pass resources down the PO edges at the sides, the program order edges at the sides, and the second property to pass resources along the RF edges going through the middle, we've got a cycle that we can pass resources around. In the program logic setting, this is enough to synthesize resources out of thin air, and we get into consistency immediately. So a simple approach seems challenging, or maybe even inconsistent. It's worth taking a step back and looking at why can't we just take the models that I mentioned that we have and instantiate existing reasoning tools, like perhaps Iris, with them. Well, there's a few different presentations of the ARM-A model. We have operational models. They are naturally operational. It should, in principle, be easy to instantiate Iris with their operational semantics. But these models are quite weird. They explicitly model the speculation that the architecture, that the hardware does, and they also include things like instruction rewinding. The notion of a program point isn't even well defined in these settings. It's not clear how you reason about these manually at all. We have promising models. These are also fairly operational, and they've been used to build logics before. The challenge with promising models is if your weak memory setting allows for load buffering, your promising model requires a certification step. These potentially require reasoning about arbitrarily much future execution. Again, this is very tricky. We want to avoid it if we can. And so that leaves us with the axiomatic models. So to give a very brief summary of how these work, we execute all of our threads sort of in program order, building up a set of memory events that those threads carry out. We have a collection we work out sort of how they're related to one another, and then we check that there exists some ordering relation called OB on ARM, happens before in some other settings, that satisfies various properties, and importantly is acyclic. So these models they're relatively succinct. They seem like they should be straightforward to formalize, but they're not remotely operational, which can be challenging for a compositional reasoning tool. My thing has stopped advancing. Okay, good. So these models are extremely global because this consistency check that OB is acyclic happens at the end of program execution. That's really annoying because lots of the information about what program behavior is allowed is only really available in this consistency check. And if we want to do compositional reasoning, we want to have that information while reasoning about only partial programs, not full executions. We can't straightforwardly just move the consistency check up and do it on partial programs because an execution that looks consistent can be made inconsistent by later events. It's very difficult to see how to sort of pre-do this in a consistent way. So to resolve this issue, we look at the axiomatic semantics from a slightly different direction, and we see that we can permute the order of the sort of check that the memory event graph is consistent and the check that it corresponds to program behavior. This gives us the OPAX semantics, which is novel, which begins by guessing a consistent whole program memory event graph before doing any execution, and then incrementally checks that that graph corresponds to program behavior. So to give a brief flavor of what this looks like sort of formally, we have two major steps of the operational semantics. Initialization. At the beginning of time, we guess a memory event graph G. This is for whole program memory event graph. It's required to be consistent with the axiomatic model, but at this point doesn't necessarily correspond to program behavior in any way. And we initially have a fulfilled event set, which is empty. Then as we execute the program, so say for an example, we execute a load instruction, we check that the graph contains all the appropriate events, so in this case, a read to the same memory address of some value, and that they haven't yet been fulfilled, and we mark them as fulfilled. If the graph, which was arbitrary, doesn't contain the events that we needed to contain to execute some instruction, those configurations are just stuck. But we don't consider this to be a failure state, we just discard those executions. I should note there's lots and lots of state missing from this configuration required to track all of the graph structure that needs to be there. This is a gross simplification. So at this point, we have in hand a semantics which, while it's not really executable, is certainly operational enough to instantiate Iris with. And I'll hand over to Zongyuan to explain what the program logic that we get by doing that looks like.
So on top of the OPAX semantics, we build a program logic using Iris. The logic is called AxSL, and they support thread modular reasoning about the ARM's memory event graphs. And to do that soundly, we need to introduce a few new Iris assertions. So firstly, we have this register point to assertion, which means that the register R has value V, and the value comes from a memory event A. And secondly, we have a tie to assertion, which essentially tie the resource P to a memory event. Intuitively, it allows us to detach the resource P from the program point. So these two assertions are very important for sound resource parsing along program order. We also want modular reasoning. So that's why we introduced our own Hoare triples that is indexed by an additional per location protocol. So this protocol phi allows us to transfer resources between threads. So when we're writing to a location, we give away resources, and when we're reading, we obtain them. To see how AxSL works, let's have a look at the message passing example. So in this variant, we have two threads. On the left, we first write 42 to the data location, and we set the flag with a release write. So the release write here induces an OB ordering between these two store instructions. And similarly, on the right-hand side, we first read from the flag, save the value to R1, and we use R1 to compute the address of the second load instruction. This is so-called address dependency in ARM, which also induces in OB ordering. So the simplification I want to prove over this program is that on the reader side, eventually, if the value we read from the flag is 1, then the value of the data must be 42. And to do this in a thread modular way, we first need to set up the prolocation protocol phi. And we say the protocol phi at data location is saying that the value of the data is either the initial value 0 or the value 42. And the protocol at the flag is saying that it's either the initial write or the release write that is PO ordered after the write of data with 42. With this protocol in hand, we can reason about this example. On the left, remember how the OPAX semantics is working is essentially checking if the program behaviors matches the graph we guessed at the beginning. So here we have a store instruction, which means there must be a write event in the memory graph. In addition, because we are writing to this data, so we have to prove that the protocol is satisfied, and can be done by picking the right disjunct of the protocol. Similarly, the release write, after the release write, we know that there's an event B, which is PO ordered after the first event A, and we can also discharge the propagation by picking the right disjunct. On the right, we first read from the flag, and we save the value to R1 register. After that, we know there must be a read event with value of V flag. We can also update the register point to predicates with V flag at C. Here, at C meaning that this value, V flags, come from the event C. In addition, because we're reading from the flag, we obtain the protocol resource. But here we have to attach the 5 flag to the event C because otherwise it won't be unsound. And next, after reading the data, we do same things. We update the registers, and we obtain the resource file of data, and we attach that to D. And here, because of the address dependency between C and D, we know that they are ordered. So that allows us to actually pass resource from event C to the event D. By doing so, we have collected all the information we want to know about this graph, and by some quite straightforward graph reasoning, we can conclude a post condition. And AxSL is also sound, but proving this is sound is quite challenging. Essentially, it's because there's a tension between two things. First is that we want to reason about program in the program order, but the induction principle provided by the ARM model is along OB. We formulated AxSL's soundness as the adequacy theorem. And this adequacy theorem, the statement is quite close to the standard Aries adequacy, but we claim that the proof is novel. We have to resolve the incapability issue mentioned by Angus by stratification. So essentially, we split what we usually do in the Aries adequacy into 2 parts, and we do that separately in 2 traversals over the program executions. In conclusion, AxSL is a very expressive program logic for user mode armory memory model, and it's fully maximized in COG using the Aries framework. We have some limitations. First, we're lacking some support for the coherence axioms, and we're missing some abstraction that can make our logic easier to use. But we do hope that our approach here will generalize, in the sense that first, the OPEC semantics can be adapted for other axiomatic memory models, and the idea of tying resources to events will allow sound reasoning of other very relaxed memory models, such as RISC-V. And one more thing, a little advertisement. If you want to see some interesting robots, here's this event tonight. You can check out. It's very close. That's all. Thank you.
Thank you. Any questions?
Thanks for the talk. In this model, did you consider any event structure-based model for reasoning about these PORF cycles while developing this logic?
So I'm more unfamiliar with the event structure-based weak memory models than I should be. I'm not sure offhand if there's an equivalent one known for ARM-A. My inclination is that there isn't, which would sort of be a problem for us. The problem though is to some extent inherently logical, right? It's if you want to be able to pass resources along both of these kinds of edge, and if you allow it, it's inconsistent in the logic. It's not. We present it in the axiomatic model because that's where it's like most clean. It's an inherent problem with the reasoning principles that you want to have in your compositional reasoning tool, which we have to sort of make changes in the logic as well. Not just in the model. Sorry, we can't avoid it just by picking a clever model. We have to make changes in the logic to prevent this inconsistency.
Okay, thank you.
We have some discussion in the Discord, but also a question. So check out the Discord thread if you want to see the discussion. But the question is, it's nice when a memory model has both an axiomatic and an operational description. Could you do this for your model?
So to be clear, we don't, well, the model we're using is the standard user mode model, for which there are already axiomatic and operational and promising models, which have been proven equivalent. The OPAX semantics is reasonably obviously equivalent to the existing axiomatic model. So it's not really a new model in that sense, and the existing models are already known and equivalent.
In the grammar you showed for the iris assertions, you had this annotation phi at the Hoare trippers for the protocols.
Yeah.
Often in iris we instead make, like, instead of annotating this syntactically, it can be very useful to make this dynamic. Like iris invariants are not annotated at the Hoare triple. You can dynamically allocate them anytime. Is there a reason why you didn't do it that way, or is it something you plan to look into? Or well, I was just wondering what's up with that.
So I think it's not very clear to us that using invariant in these weak memory settings is sound. So in particular, if you want to get some resource out of the invariant, it had to be guarded by some stuff like the tied to assertion I've shown to you. Otherwise, you cannot just naively use that resource from the invariant and pass that along PO.
Right, but this is about hiding, right? Like when I do reasoning in a program logic, I might want to have a higher order function that returns a closure, and I want to hide the invariance that the closure relies on, and therefore I don't want to have annotations at my Hoare triple. So if I imagine a language in this memory model that wants to do hiding, I wouldn't want these annotations. I don't see how that would be related to getting resources in or out. That seems orthogonal.
So it's not clear, at least to me, that you can do it's not immediately obvious how you can build protocol-like reasoning out of just invariants in a weak memory setting. If you want to do this sort of protocol resource transfer, just using invariants.
I'm not saying just using invariants. I'm saying make it dynamically allocated.
Sure.
Have a view shift which you pick a protocol and then you have an assertion which says this is my protocol instead of having it syntactically annotated. Like IGPS still has hard-coded protocols, but they're dynamically allocated, right?
I suspect, but have not proven, that you can give a single static protocol that sort of uses Go state to keep track of a dynamically changing protocol. I think you can do this. I think it's very similar to the way you'd expect it to work with IGPS. We haven't proven it in this setting, but I don't see any reason why it wouldn't work.
Okay, thanks.
Do we have time for another question?
Yeah, one more question.
Thank you. About the OPAX semantics, could you clarify why it's important to guess the whole graph ahead of time and then progressively work into it, as opposed to gradually building the graph?
So there are a couple of different things you can do, and they work somewhat similarly. There have been pencil and paper versions of this logic where you guess sort of incremental chunks of the graph as you go along. I think it's basically equivalent, but harder to write down. It's important that you have sort of enough of the graph to keep it consistent at all times, which might be, even if you do this incrementally, you'll often need to guess events a long way in the future. And once you're doing that, it didn't seem, it seemed like you might as well guess the whole thing at once if you're going to be guessing unknown things and having to discard executions anyway. You might have to do that if you want to reason about infinite executions, but there are fun other problems with infinite executions in these settings anyway, so we sidestep that a little bit.
All right, let's thank the speakers again.